study. Thank you so much for coming and accepting our invitation.
Thank you. Thank you for inviting me. It's really great to be back to IFT and ICTP. So if you don't know me, I'm Matheus Hostert. I'm a postdoc at Harvard. In a little bit, I'm moving to University of Iowa for a faculty position. And I know South Americans are actually really good, have very strong foundation in theoretical physics. So if you're looking for PhDs and postdocs, keep an eye out for that. OK, with that out of the way, let me also say that I'm going to try to take a step back and talk about the very basics of BSM with neutrinos. There are two ways to do it. One is about the foundation of why we think there is beyond the standard model because of neutrinos, and that will be neutrino masses. And the other part will be, what can you do to discover or constrain BSM using neutrinos? So one is about neutrinos themselves, and the other is about using them as a tool for BSM. OK, can I start by kind of warming up and trying to get you to tell me what are some of the reasons why we think BSM is a thing? Why do we think we have to go beyond the standard model? Dark matter, very good. Gravity? What else? What do you mean? Neutrino masses. Okay. Anything else? Hierarchy problem. Which one? The Higgs? Strong CP. All right, I think I'll stop there. There are probably more. But the point I want to emphasize here is that these problems, you can always phrase them as incompleteness problems. The standard model is actually not wrong. It's just incomplete, insufficient. And that's why we talk about beyond the standard model and not replacing the standard model. So, and that doesn't mean that this is not a worthwhile effort. I mean, we know general relativity does not replace classical mechanics. It just extends it. But it brings about a very big change of paradigm. So does not take anything away from this. For these kind of 1.5 lectures, I'm going to focus on neutrino masses. And I want to do it in a way that is as clear as possible, as basic as possible, so to avoid any confusion as to why we say they are BSM effects. So stick with me for that. For the ones that know a lot about quantum field theory and the standard model, just sit back, relax, and just enjoy the ride and how beautiful the standard model construction actually is. OK. You could say that neutrino masses are like a footnote to the standard model. Maybe you just add some new particle. Direct neutrino masses are there, and that's the end of the story. But actually, it has some pretty big implications for fundamental symmetries, what actually are the new particles and new propagating degrees of freedom. And I think it's actually worth exploring. So let me start with things that you should know. Let me start with the warnings here. The first one is that I will use natural units. So I think probably most people are familiar with that. The other one is a little less conventional choice. OK, don't worry. I'm just dropping my factors of 2 here and there. That will also happen. If that bothers you, this is going to bother you even more. I'll also drop factors of I here and there. So everything that I will do as far as the standard model construction is schematic, following mostly 2-component spinor notation. If you want to go back and reconstruct it carefully, go to the reading materials that are online. There's lots of resources there for that. OK, let's start with things that you should absolutely know. The first one is that the standard model has a Lagrangian formulation with an action. And this action has energy to the 0th type of units. So it's dimensionless in natural units. What this means is that since the action is an integral over all space-time volume of the Lagrangian, which will be our main kind of ingredient containing all of our fields and other ingredients. This means that because the volume of our space-time has units of e to the minus 4, the unit of the Lagrangian, which I'll write many of here, will be energy to the 4th. This is very important. Many of you are very familiar with that, but it will enter into our discussion many times throughout these lectures. This has to be true. Okay, in 4 dimensions, at least. The other thing is that the Standard Model is a chiral theory. And what that means is that if I write down the symmetries behind the Standard Model, which will stand for the forces and the mediators, there is asymmetry that actually doesn't care about whether you're left or right. That's SU3 color, that's QCD. There is a symmetry that absolutely cares if you're left and right. In fact, it only cares if you're left-handed fermion. And finally, there's a U1 hypercharge, which is, in the end, going to give you this combination here is going to give you the photon. So it's the fact that the Standard Model has this force, this symmetry in there, differentiating left and right maximally, that makes us say it's a chiral theory. And it's also going to play an essential role as to why neutrinos are strictly massless in the Standard Model. The other thing I want to say here, I want to emphasize this group, this symmetry group, is always conserved. Always. But the Higgs. The Higgs mechanism hides the symmetry and doesn't explicitly break it. So that will also be important for our discussion. So whatever you're doing, you're model building, you're doing phenomenology, you should always ask yourself, am I violating any one of those conditions? And if you are, you're breaking one of the pillars of the Standard Model, and then yes, you will be replacing the Standard Model with something new, not necessarily extending it. So I'll get to that in a bit, but the point that I'm trying to make is maybe this is more for the people in the know, but part of this symmetry is actually broken by the Higgs mechanism, but it's actually not fully broken. It's not explicitly broken. It's through a mechanism called spontaneous symmetry breaking, but all that mechanism does is not actually break the symmetry, it just hides it somewhere that, you know, in our world here we can't really have access to. But if you look carefully into where the Higgs talks to other particles and so on, the symmetry is actually conserved. This is also true if you look at QCD, also spontaneously breaks part of the symmetry, but in the end, they are always conserved. Okay, any more questions? On this point, since the Standard Model is a chiral theory, I'll also tell you what the ingredients are. The first one is this little package of the electron neutrino and the electron inside of what I'm going to call the lepton doublet. And what this means is that the electron, at least the left-handed version of the electron that we are all used to, and the neutrino always come together in this very specific fashion. Okay, so this should be obvious for some of you. For those that this is not obvious for, just remember the Standard Model likes to differentiate one type of chirality from the other. And what this package here is doing for you is it's keeping types of particles inside of the same unit, and they talk to the Standard Model forces in the same way. There will also be, for the same generation of electron neutrinos and the left-handed electron, there's also going to be what I could call a right-handed electron. That's usually how you would see that. But in these lectures, I'm actually going to call this the left-handed positron. There are very good reasons to do that. It makes our discussion much cleaner, and it makes the discussion of fermion masses much more transparent. This would be a right-handed fermion if it was a particle, but because it's an antiparticle, it actually turns out to be a left-handed fermion. So the way you can phrase it, as the Standard model is Cairo, is it only couples to the left-handed particles, but not the left-handed antiparticles in this language. Okay. There are also other doublets for the nu mu and the muon, and the same for the nu tau and the tau. And here as well, a left-handed anti-muon and a left-handed anti-tau. Okay. Finally, we also have the Higgs. The Higgs happens to come in the same type of package because it talks to one of these symmetry factors, namely the one that differentiates left and right. In this case, it's a scalar particle, so it doesn't make sense to talk about left and right, but it still comes in this little package with charge components and neutral components. And this, at low energies, through the process of spontaneous symmetry breaking, which we can talk about, will look like this. So initially, the Higgs is actually something that carries 4 degrees of freedom. These things are complex fields. When you go to low energies through the spontaneous symmetry breaking, the Higgs mechanism, you end up with something that you can basically ignore the charge component and imaginary component. You end up with something that has these 2 things here, and we'll talk about what they are. The first one is actually the field. So this is the Higgs field, and it's responsible for creating and annihilating the Higgs particles. So this is where you get quanta from. And the second thing is the VEV, which stands for vacuum expectation value of the Higgs. And if you want, this is like, if you were to ask what is the value of the Higgs field somewhere in space, let's say there's some field here. This is the Higgs. If you were to, at any point, look at what this field looks like, on average, it typically has this specific value. This is a constant, and in fact, we know what it is now that we've measured the Higgs and its mass. It's 246 GeV. So this package of the Higgs that had multiple degrees of freedom gets simplified at low energies to something that creates Higgs particles and a constant that has units of mass. Okay. The mechanism through which this happens, we know how it works. We don't know why it works. But the very basic way to think about it is if you were to draw the potential energy associated with the Higgs as a function of the value of the field, this potential energy looks like this wine bottle potential. And it just so happens, we don't know why, but it just so happens that the minimum of the energy of the universe happens at a position where the Higgs value is not 0, but actually this finite constant V. So it's very simple terms what the spontaneous symmetry breaking means. The universe would like to be in this position for the Higgs field in order to minimize energy. Any questions so far? Okay. Also a reminder, the field is basically a little machine. You put in energy, it gives you a little particle, it travels, and this particle can also be absorbed and will release energy back to you. So, yep. Esse zero aqui, well, I can answer in Portuguese. Is English okay as an answer? Okay, so everybody can follow. This 0, 1, this 0 entry is actually quite special. It's a choice that you have in the theory. And essentially, it all boils down to the fact that the theory is over-constrained. There's too many things. There's very little things that you can do given the amount of symmetry that you have. And you have a choice of where to put these degrees of freedom, including also the complex entry here. And you can actually shift them to other particles that we'll not talk about. If you want to be more specific, the Higgs plus and the charge conjugate Higgs minus become the longitudinal modes of the W bosons. And the imaginary component here becomes longitudinal mode of the Z boson, or the neutral hypercharged boson. So they get absorbed by other particles in the theory because I have a lot of freedom given the amount of symmetry in the theory. So it is a redundancy of the theory that allows it to shift the degrees of freedom around. This is not necessarily zero always, it's a choice. So just to say that, at low energies, I'm perfectly allowed to make this choice, if that makes sense. We can talk more about that in the general question session, because I think it's a little bit more advanced. But the main picture that I want everyone to follow is that these are the ingredients that I will actually care about. I'm not going to talk about quarks or the mediators so far. In the lepton sector, you have these little packages and these individual fields for the left-handed antiparticles. And then you have the Higgs field, which is also coming in this little package. But at low energies, I'm perfectly allowed to treat it as this quantity here, where V is a constant and H is, thank you, and H is the field that creates and destroys Higgs particles, given or giving away energy, receiving or giving away energy. Okay, third thing you need to know, actually this one I'll write in the center because it's very important. Is how fermions can get a mass. The first way in which a fermion can get a mass is called a Majorana mass. This mass is a coupling between a particle and itself. In diagrammatic ways, all it means is I have one particle, which can be any one of these, and it's coupling to itself through a term in the Lagrangian that will look like this means contains, so my Lagrangian contains the term. This has units of energy, so mass, let's say GeV. Let me put E actually. And this, each fermion inside of this has a unit of, I should have written maybe over here. Chi has units of energy to the 3/2. And any other scalar particle has units of energy. So this is fermion and scalars, and boson, sorry. And now you can see that this mass term has a unit of energy at the front, and then 3/2 squared, because there are two fermions. So e to the 3rd, and that gives me e to the 4th power, as we want in our Lagrangian, which has units of energy to the 4th. I cannot emphasize enough that this is actually a very simple mass term. Only takes one fermion, one type of fermion, and then you just couple it to itself. There is one problem, though, which is that if this fermion carries any quantum number, electric charge, lepton number, whatever it may be, this coupling with itself actually violates that lepton number by 2 units. So in terms of the quantum numbers, we write arrows to indicate this is, would be a particle, and this would be antiparticle. So overall, any quantum number associated with chi is violated by 2 units given this interaction. You can see that from the Lagrangian. There's some interaction of the fermion with itself. If this carries like a unit of charge, this will carry the same unit of charge, and there's nothing else to cancel that, okay, because this is just a constant. So the simplest mass term, but unfortunately, it violates charge. This doesn't have to carry any charge, in which case you could just write it down, and it's perfectly okay, and a very minimal thing to write down. The other type of mass term is a Dirac mass. This one we don't know if it's realized in nature for fundamental particles. This one we know it's absolutely sure it's realized in nature, but in a very weird way that we'll see through the Higgs mechanism. And the way this mass works is you take two separate fermions, let me call this eta, for example, and you couple them to each other. So in a sense, it requires more than the Majorana mass, because now you need two separate types of fermions. Remember, these guys are not the same as these guys, even though I named them very similarly. We'll get to that in a second. In your Lagrangian, the mass term, typically I'll write as MD, and you'd write chi eta. So it's coupling the two fermions to themselves, with each other. Now, if charge Q of chi is minus the charge Q of eta, I am okay, and I'm not violating any of the quantum numbers here. A Majorana mass will always violate any quantum number associated with the fermion. A Dirac mass may or may not violate quantum numbers associated with these fermions. This is very important. It also depends on the choice of what fermions you're coupling to each other, whether Dirac mass violates the charges or not. It just so happens that in the standard model, the Dirac mass does not violate any important quantum numbers, but in principle, you could. So this is the biggest difference. Q can be conserved. Any questions? All right, now let's talk about lepton masses in the standard model. So we'll take these ingredients and ask how can we put them together in order to either create a Majorana mass or a Dirac mass. It doesn't have to be true. If this is true, then Q can be conserved, or Q is conserved if this is true. Maybe I should clarify. If otherwise, that's not true. So you'd violate the quantum numbers. All right, so let me first actually not talk about the standard model just yet. Let me just clarify my notation a little bit by going back to quantum electrodynamics. So in QED, all you have are electrons and photons, and the electrons are massive in QED. And the mass term that you write in QED, the ingredients are E and EC in my notation, just looks like ME, E, EC. So I'm coupling the fermion electron, left-handed electron, to the fermion left-handed positron. These are two separate things in principle. Before I wrote this down in QED, the left-handed electron and the left-handed positron are actually completely separate fermions. They may not have anything to do with each other. I could have called this A and B if you want. It's only because we're coupling them to each other that we call both of them the electron, and they pertain to the same propagating degree of freedom. One way to think about this is you have an electron field, and there's an electron propagating, let's say, in the state E. This can interact with the field, and these fields are basically on top of each other everywhere in space-time. The way to think about it is the electron and the the positron are essentially scattering into each other. And this scattering creates a mass, a rigidity to the field That means you need to put in more energy to create a quantum than you would otherwise. So that's QED, and I was perfectly okay writing these two down because the mass of the positron, sorry, the charge of the positron is opposite to that of the electron. Well, I guess what you call a particle-antiparticle is also kind of dependent. I would say it doesn't always have to have different charges, and you can also have a particle that has plus electric charge, for example, or a particle that has minus electric charge. The proton we call a particle, and it has a positive electric charge, but the positron has a positive one, and we call that an antiparticle. So in a sense, it's kind of convention dependent. What really matters at the end of the day is the relationship between all of the charges in the theory. Oh, you could. You absolutely could write down that mass term in QED. It turns out that because of the symmetries in QED, because the U1 is conserved, if that means anything to you, all of those mass terms, if you were to write down all of the combinations between all of the electrons, the muons, and the taus, you can always diagonalize them back to what you would get if you were to write down electron, muon, and tau separately. So the gauge symmetry inside of quantum electrodynamics is so constraining that even if you were to write down all possible mass terms for the fermions, you can always rotate things around and maintain the same physical consequences. Yeah. If I'm not making sense, just let me know, and we can talk about it. All right, this is QED. And you note that in QED, the electron appears here on its own. And that was the only reason why we could write down this mass term, which we now recover E and EC. But in the standard model, that's no longer the case because the electron is inside of this little package, our lepton doublet, and the positron is here on its own. So, well, you could ask, how can I combine the two things? First of all, I need to make sure that my Lagrangian is a scalar. It's just a number. So it cannot be a vector like this thing, this doublet. So I would have to contract this with something else. And before we go to the right answer, let me try to build the wrong answer. Let's say you take the lepton doublet and you say, look, it's a vector, you just contract it with itself. The right way to do it is you dot it in a very specific way to maintain gauge invariance. And at the end of the day, you're going to end up with something that looks like nu E. Let me write down here. Nu E minus E nu. Where this tensor is just 0, 1, minus 1, 0. If you think enough about group theory, you convince yourself why there has to be an antisymmetric tensor there. But the answer is that this is the only thing you can write down in order to get like a scalar at the end of the day, something that doesn't carry any left charge. The problem with this is we've contracted the two things together. But now you see you have a neutrino and you have an electron. As far as our mass rules go, that's not a problem. That's a Dirac mass between one type of fermion and another. But there is an additional problem here, a separate problem, which is that the neutrino carries no electric charge, and that is conserved in nature. But the electron does carry an electric charge. So our rule that the charge of the two fermions in the Dirac mass have to be opposite, the same but opposite in sign in order to conserve that charge, are being violated by this mass term. Any questions about that? Okay, so this doesn't work. We tried to construct a singlet out of that, a scalar value, and it didn't work because of charge conservation. But what does work in the end is something that looks, and I could have tried to do the same with the electron. But I would violate electric charge by 2 units in that case. So it turns out that the properties of this symmetry group are such that the only way you can contract those two packages together to get a scalar variable, something that is a singlet under that symmetry group, is using the epsilon tensor here. You could build other combinations that will not be scalars, they will be vectors. And one way to think about it is when you add add two spins together, you basically have two vectors, up and down, right? That's your vector. And when you add them together, you can either get something that is spin 0 or something that is spin 1. That's the spin 0 solution, and that's the way you construct it in terms of the vectors. L. That's a 1 here. It's just the antisymmetric tensor. Yeah. A fancier way of doing this is like SU2 generators come with Pauli matrices, and you'd have Pauli matrices in places. But if you use epsilon, it's basically enough. We'll get there. You're stealing my thunder. Good. So I could have written down these terms with the same fermion in themselves, the same thing with the lepton doublet there, but they violate charge. And as we know, one of the pillars of the standard model is that that symmetry group there and the charges associated with them is actually, at the end of the day, always conserved. But this combination turns out to conserve all of the charges in the theory. I'll put a transpose there. And if you expand this out in terms of the low energy Higgs package, which has only the bottom entry, you will get something that looks like Higgs plus Vev, square root of 2, and then write square root of 2 there? I did. Times the electron, which comes from the lepton doublet, and the left-handed positron. And now that conserves electric charge, and it's also a scalar variable, if you will, in the sense that I contracted a vector with another vector, and that's okay. That's a perfectly okay interaction term in my Lagrangian. I haven't set a mass just yet. But if I expand this out, I will see that there is a term that looks like EEC plus a term that carries this constant V. Diagrammatically, the way you would think about this is as a mass term. Initially, that interaction in terms of the Higgs vector, the doublet, and the lepton vector, or the doublet, and the left-handed positron looks like that. So there's the 3-particle interaction. At the low energies, however, I get 2 new types of interactions. One with the Higgs field that creates Higgs particles, and another with this kind of constant V, which we said is the expectation value of the Higgs. This looks a lot like a mass term, except there's this weird like cross here. And what this means is that the mass term in the standard model comes exclusively from this constant V, and that the scale of that constant and the size of the couplings that appear in front of these operators actually fully determine the lepton masses and all of the fermion masses in the standard model. And in order to get a mass term, you need to go through the Higgs, and you need this insertion here. So when I said, even though we hear that the Higgs mechanism breaks this part of the symmetry of the standard model, what it's actually doing, it's hiding part of the charge of that symmetry group inside of this insertion there. So if you were to take standard model processes and actually carefully track the Higgs insertions and the VEVs, you would see overall the full charges of the standard model are always conserved, except some of them are hidden inside of the Higgs field through these VEV insertions. So here's a prediction of the standard model. All fermions are massless. Unless the Higgs develops a vacuum expectation value, which does happen in nature. And that's something we confirmed in the LHC. This is very bizarre. Not only is the Dirac mass kind of weird, it couples two different types of fermions, but now not only we have a Dirac mass, we also have a Dirac mass that only appears at low energies and only because of the Higgs. It's weird, makes me uncomfortable, but that's the way the standard model has chosen to do things, and that, as far as we know, that's the way where most fermions get their masses in nature. Any questions about that? If not, then we'll talk about neutrinos. I shouldn't be deleting the gauge symmetry. It's just so nice. The cross just means that the interaction term in your Lagrangian has three things that are involved. There is the electron, the left-handed positron, and this constant. It doesn't really mean anything other than like whatever is giving you that cross here that we usually drew just on the line of the fermion for the masses is actually coming from the Higgs, in particular the Higgs field and its expectation value. That's all it says. I think it's a nice way to just kind of hide the charge in there. Okay, neutrinos. First thing you note, if you look at the particle content of the standard model, is that the neutrino is inside of that package. And that should make you uncomfortable as far as masses go, because we try to build masses out of those packages before, and we had to use one of the lepton doublets, the Higgs, and then another different kind of thing. But you don't see another different kind of neutrino in the standard model. But even then, it should also make you uncomfortable because the VEV is sitting down here instead of up there. So there's more work that you have to do in order to get neutrino masses. But that's actually quite simple. It turns out that you could just define a field that I will call Higgs tilde. It's again that antisymmetric tensor times the Higgs. And this looks exactly like the Higgs we had down there, but with the entries flipped. Okay? Turns out this is perfectly equivalent to the Higgs as far as the SU2 left is concerned. For neutrinos, then I can write down something that looks like that, which if you multiply this out, you'll see that it picks out, again, that combination times the neutrino field. I'm not going to specify what family I'm going to be talking about for now. So usually from now on, I'm mostly thinking about a single generation, single family model. So that's nice. We kind of isolated the neutrino by itself. This thing, actually, it's a spinner. It carries indices, so you have to contract with another spinner. You cannot just leave that alone in the Lagrangian. So I need another thing to contract this with. I don't have a left-handed antineutrino in the theory, or you would usually sometimes see this as a right-handed neutrino. In just my notation, I've made that into an antiparticle. So that's not in our theory. And before giving in to temptation and just adding that, let's try to work and see what we can do just with this term. First thing you could try to do is, again, the game of trying to contract the lepton doublet with itself, but we saw that that doesn't actually isolate the neutrino. That talks to neutrinos and charged leptons at the same time. So that trick is not going to work. So let's try to use this one. So very schematically, you could just square that thing. And that will look like that same combination squared, because I've basically squaring this entire thing, and then nu. That's how I run a mass term. You see it's a field coupled to itself. But now it has this bizarre property that it goes like the square of that combination instead of linearly with it. Diagrammatically, you would write this term like that. In terms of the full kind of components, the full ingredients, it's L, L, H. And then at the end of the day, this is going to have two terms. The first one that comes from those crosses, actually three terms, nu. There's also the same term where you get only one of the crosses, and this is the Higgs, nu, and then finally you also get two Higgses. So this trick of squaring that interaction in my Lagrangian gave me all of these things. One of them looks like a mass, so great. But before declaring victory, let's count the energy dimensions of this thing. That's a fermion, so we knew that that has to go like E3/2. I'm squaring that fermion, so E cubed. And that's a boson, a scalar, and that goes like energy, and I'm squaring that. So that's overall as units of energy to the 5th power. But our Lagrangian has units of energy to the 4th power, so what happened? Yes? 3, because if you expand out this square, you get one that goes like Higgs squared, another that goes like Higgs Vev, and then one that goes like Vev squared. Okay, so now this thing has 5 units of energy, but we want 4. The way to fix that, and I'm being super crude here, is just add a new energy scale to my denominator. Okay, so that's, I'm not even going to put the 1 there. That's just an energy scale in the denominator. Now, that's dimension 5 minus dimension 1, dimension 4, so that can go in my Lagrangian, and you can write that down. At the expense of not knowing what this thing is. We just don't know. We'll talk about that a little bit towards the end of this lecture, but at the expense of actually being able to write down a mass term in the standard model for neutrinos, I had to introduce something new, which is this scale lambda. As it turns out, this scale lambda corresponds to a scale at high energies compared to the typical energies involved in this interaction, which is actually going to generate my random mass of the neutrinos with actual physical degrees of freedom and physical particles. Right now, this is not really physical in the sense that I haven't added any new particles. I just added a new scale. Provided all of your momenta of your theory are typically below that scale, so all of your energies are below that scale, this is a perfectly fine way to do calculations. But we still like to know what this is and what kind of physics it comes from. Another way to think about this is lambda as a distance. So 1 over lambda is also some kind of distance. And provided you're not probing wavelengths that are smaller than this distance, so provided lambda is greater than L, you're not resolving the new physics associated with this new scale lambda. This is called an effective field theory. And it's, just as the name says, something that is effective. You don't have to specify the actual degrees of freedom behind the new physics here. You just kind of insert arbitrary coefficients to these interactions and carry them through in your calculations. This operator does not need a right-handed neutrino. It only needed the left-handed neutrino, the actual left-handed neutrino in the Standard Model, and it's called the Weinberg operator. It's one of many that you can write down, given all of the fields of the Standard Model. And it turns out it has dimension 5, as we counted before. And it is the lowest dimension for an effective operator inside of the framework of the Standard Model. So at dimension 5, actually only this operator exists. So it's the lowest dimension and the unique one at that dimension. And it turns out to give neutrino masses. So that's kind of a very interesting observation that just carrying out this very straightforward procedure, sticking this effective mass in the denominator, it turns out that that operator, this entire thing, is unique at that dimension, and it turns out to give neutrino masses. So the conclusion from that is that one of the first evidences of physics beyond the Standard Model appears at the very next order in this effective field theory, in the sense that at the lowest dimension of effective operators, it's the first thing that appears. So that's an interesting observation. This is also part of why many theorists share kind of a, I wouldn't say a prejudice, but kind of a expectation that neutrino mass is of a Majorana type, because this mass is of Majorana type. Okay. Any questions? How am I doing on time? Half an hour. Okay. Now let me go over here. I don't want to. Yeah. Yes. So what are the quantum numbers of neutrinos? There's no electric charge, so that's okay. We haven't violated something that is conserved in nature. I'm not violating the weak charge of the neutrino, the one associated with weak interactions, because whatever weak charge you get from these two terms is actually canceled out from that thing there. That's why I said it's always conserved, as long as you track the Higgs insertions everywhere. In fact, whatever charge is here being violated by the delta Q equals 2 Majorana mass is actually being absorbed by the Higgs field. So in the end, none of the quantum numbers that we know have to be conserved in nature are actually being violated by that interaction. But your question is very appropriate, because there is one quantum number associated with neutrinos that we don't usually impose anything on, and that's Lepton number. So a neutrino has Lepton number of 1, an electron has Lepton number of 1, a positron would have Lepton number of minus 1, and so on and so forth. And if you look at that interaction, nu, even though the weak charge can be absorbed by the Higgs field, lepton charge cannot, because the Higgs is not a lepton. So if lepton number at this point is 1, the lepton number at the end is minus 1, and I violated lepton number by 2 units. This is a hallmark of Majorana masses, and it's one way in which you could hope to discover that this is the correct solution behind neutrino masses and not the Dirac-like mass. Yes, great question. It turns out we have never really done an experiment directly where you see the effect of the neutrino mass as the primary thing that you're observing. So we've never really, first of all, measured the neutrino mass directly, the absolute value. And we've never seen neutrinos where the mass is the dominant contribution to their energy. And that is to say, we've never seen neutrinos that are non-relativistic. Every time we produce neutrinos in the lab, every time we detect them, produce them in accelerators, they're always ultra-relativistic, so the momentum is the thing that matters. And it turns out to tell these two apart, you really need to know something about the mass, but the mass rarely matters for the things that we can detect with ultra-relativistic neutrinos. But we'll get to that point. Just to answer you very quickly, what Pedro was discussing today about neutrinoless double beta decay, it's a process that violates Lepton number by 2 units. And if you observe it, you have very strong indication that neutrino masses should be of Majorana type. So very quickly, so I don't just say words. The way this works is you could imagine there's some nuclear physics up here, some nuclei. There are 2 W bosons. And you emit 2 electrons. Now I'm drawing like the actual particle you're observing, 2 negatively charged electrons in your experiment without any other anti-lepton in the process. And if you analyze this diagram carefully enough, in terms of particle number, this is L equals 1, this is L equals 1. And this thing in the middle, because it's a W boson, in this case minus and minus, because it's a W boson, it's a minus and minus here. The neutrino in the middle cannot be just a single type of lepton. It has to flip lepton number in the process. And the way we denote that is through a Majorana mass insertion. So it flips a lepton number of +1 to -1. And in the end, it allows you to do this delta L equals 2 process. We can talk more about that later. This is one way you could do it. Or if you had non-relativistic neutrinos, for example, the C nu B, you could just count the number of degrees of freedom of that particle. And in one case, it will be 2, and the other will be 4. And 2 is not equals to 4. But, yeah. OK. So that's weird. That's a Majorana mass. It's in a sense in the standard model, except you've learned about a new scale lambda UV. And you'd like to know more about that. Now let's talk about the alternative and give in to temptation and just add the right-handed neutrino or the left-handed positron. And in that case, now I can write the same thing I did with the electron, LHE, but now I want LH tilde, the one with the swapped entries for the VEV, and then nu C, this new particle nu C. Again, there's some arbitrary coefficient there. Now the same thing, you're going to get a mass term that I'm going to call this MD, and MD again contains, because there's also an interaction with the Higgs, but MD will be determined by the VEV and this coupling. So that's a Dirac mass. This is one way in which neutrinos could be Dirac, 10. And all you had to do is add this new particle, nu C. What are the consequences of adding this particle? They're actually pretty big. So in ancient Rome, they had a principle in law saying that whatever is not forbidden is allowed. So if you haven't told me what I can't do, then I am allowed to do it. In particle physics, the lemma is actually different. Whatever is not forbidden is mandatory. So very authoritative. That's the way we build theories. And you'll note that this particle here, nu C, was not in the standard model. And it turns out if you add it, the most naive thing that this particle will do is absolutely nothing. It doesn't couple to the weak force. It doesn't have electric charge. It doesn't carry color. So it has basically no quantum numbers that we expect to be conserved. And since that's the case, then you could have just written nu C for a Majorana mass. And this is perfectly allowed. You can tell me that it's forbidden, but then you have to tell me why, and in that case, you can say L is conserved. L being Lepton number. We know this would violate Lepton number by 2 units. I never told you Lepton number had to be conserved in the first place, so it could just be there. But if you tell me now the Lepton number is conserved, then I am not allowed to write that down. And if L is conserved, then mu has to be exactly 0. And neutrinos behave just like any other particle in the standard model, and are of Dirac type. If L is not conserved, and in fact, if it's violated by 2 units precisely by mu, if I'm allowed to write this down, then we've learned something new. Even if L is conserved, we also learned something new. The standard model never told you anything about Lepton number. In fact, in the end, it just so happens that Lepton number is conserved in the standard model, but no one actually asked for that. But if you do ask for that, then this mass has to be 0. Okay, one last thing. Yes, so in the standard model, Lepton number as a quantum number is conserved by accident. No one asked for it to be conserved. Electric charge has to be conserved, weak charge has to be conserved, color, but Lepton number is not. Lepton number is conserved by accident. You don't require it to be the case. Okay? When you add this new particle, you have an ambiguity as to whether or not you can write this mass term, this Majorana mass for this new particle. If you write it, you violate Lepton number, which is okay. No one told you it had to be conserved anyway. It was just an accident. If you don't write it, then Lepton number is conserved, but you violated that principle. And the way to fix that is to say this is forbidden because Lepton number is a symmetry and I have to impose it. If we impose the symmetry, the mass is not there. If you don't impose it, there's no reason why it shouldn't be there. So it's mandatory. Quando esse aqui é 0? When that's 0, then neutrinos are Dirac. Yes. Because the only thing I have is this mass term that connects nu with nu c, which are 2 separate fermions. They are Dirac. If mu equals 0, it implies that neutrinos are Dirac. What if mu is not 0? Well, you have 2 options. We'll explore them a little more detail tomorrow, in particular their phenomenology. The first one is where mu is much smaller than the Dirac mass. In that case, we'll see this more carefully tomorrow, but just to end on this note, neutrinos are actually 2 different types of states with a mass splitting that is given by mu and their overall mass that is given by the Dirac mass. We'll show this tomorrow. If mu is much larger than the Dirac mass, then neutrinos are 1 light neutrino and 1 very heavy neutrino. This one will carry mass mu, and this one will carry a small mass that looks like md squared over mu. You can show this by collecting both of these mass terms inside of a matrix. So nu c, nu c. This is always 0 unless we write the Weinberg operator, which we won't, because we're writing everything at the dimension 4, here and here. This is the Dirac mass, which couples nu with nu c, and it has to be symmetric. And this is the mu parameter. If you diagonalize this matrix under this assumption, you get a spectrum that looks like this. There are 2 states. They're separated by a small mass mu, and the central value of this is the Dirac mass. And if you diagonalize under the assumption that mu is much larger, you get that one of the states basically has this entire mass, and the other state gets what's called seesaw. And that is the seesaw mechanism. It's a hierarchy of scales between the Majorana mass and the Dirac mass. And it's a way to explain what Pedro was telling us, why neutrino masses are so small and so different from everything else. It could just be that because of a new scale in nature, namely mu, we are suppressing the neutrino masses through this mechanism. It would be unique for neutrinos to do that. No other fermion in the standard model allows two types of masses, Dirac and Majorana, mostly because all the other fermions carry electric charge, and that is conserved. And at the end of the day, you cannot write down a Majorana mass for them. So you only have one type of mass, which is of Dirac. It is not. So in the standard model without this operator, which is bad because it's dimension 5, but it's an effective field theory, so it's okay. We don't ask too many questions. And if I don't add the right-handed, the nu C field here, neutrinos are massless. And that was a prediction of the standard model back when it was first written down. It so happens that they are not because of what Pedro explained to us of neutrino oscillations. But it could have been the case. It would have been none the wiser about masses if they were very, very small. Okay, I think I'll end here because I'm out of time. But tomorrow we'll pick up from this point and explore some of the consequences of the seesaw mechanism and explore also this option. So thank you.
Further questions?
All right, I went very fast through this. So we introduced this new particle. We were already able, once we introduced it, to write down a Dirac mass term because of the Higgs. So that's there. If I were to write down a matrix containing all of the mass terms in my Lagrangian, I should have specified, by the way, this is in my Lagrangian. Okay? So if you multiply this out, this is just a series of like numbers. If you put them inside of the matrix, you get these Dirac terms here, connecting nu and nu C. Okay? Now, because I've added nu C, there was no reason why I should not write down this Majorana mass term, and that goes inside of that entry of the matrix. So that's what it looks like in all generality. In principle, there could be another entry here coming from the Weinberg operator, but we won't do that just now because we want a full theory, not an effective one. If you diagonalize this matrix, if you go to the mass basis, because right now what's going on, and maybe this is what I didn't explain, what is going on is you have these two fermions, there are masses that couple them to each other, and then there are masses that couple one of them to itself. That's not the propagating degrees of freedom, because the mass of a single particle is not well defined in this picture. So you have to diagonalize this mass matrix, and your new basis you can call this nu plus, nu minus. And in that new basis, in this limit, you will get something that looks like md squared over mu, and something that looks like mu over here with zeros. Those are your propagating degrees of freedom. They carry different masses. I actually think this is the other way around. But this one is the light neutrino that we know of. We can identify with the thing that we're producing in our experiments. And this one is some new state that carries a Majorana mass mu. This thing can be anything. For example, it can be 10 to the 10 GeV, and we'll never know. All that means is that you're suppressing light neutrino masses. And the numerator can be very large, but because the denominator is even larger, they're very small. We'll put numbers next time. Does that answer your question, by the way? Okay. Yeah. I think there was a question there. No, it was not. Oh, there's one there.
Well, I don't know if it makes sense, but what if the Majorana mass and the Dirac mass are in the same order?
If they're of the same order, you have this really weird case where this scenario is actually, let me replace this by tilde, which is what you're saying. In this picture, you have a system of two propagating degrees of freedom that are separable. Like you can actually see the separation between the two in the spectrum here. And basically what that would mean is that there would be way more oscillation frequencies than we actually know of. The reason why it's okay to take this case and still have like two states is that the splitting between these two states is so small that basically virtually all of the time they behave like a single Dirac particle. The Dirac particle is the limit where this goes to 0, and then it's actually two different fermions propagating with degenerate masses always on top of each other in a sense.
Okay, thank you.
That's not this case here is not useful phenomenologically because we know it's not realized in nature. The other two cases may be realized.
Further questions?
There's one here.
So could you elaborate more about why it's mandatory and not just allowed? Is it a model building approach? Because for me, it looks like it could be the case that you only have the Yukawa coupling and the Dirac masses.
I think it starts to get philosophical really quickly, but the thing that I will say is the theory that we know is correct, the standard model as we know it's correct, maybe incomplete, but it's correct. Everything in it is built so that you introduce symmetries and they over-constrain the system, forbidding everything else that does not happen in nature in such a way that everything that is forbidden does not happen and everything that is allowed does happen. That did not need to be the case. Like, for example, and in fact, there are cases where that does happen in the standard model of things that are not necessarily forbidden, but for some reason happen to be very small. The strong CP problem is one of them. Neutrino masses may be another. So I don't think it's like necessarily like, it's the approach that we take to building theories. Whether it's the right approach or not, I think it's more kind of philosophical. It's worked really well so far. That's what I can say.
Further questions on this side? No? So let's thank the speaker again.